In this video, I will teach you how to calculate arc length, the length of a piece of a curve. This is a BC only topic. In geometry and pre-calculus, we always thought of arc length as the length of a piece of a circle specifically. In calculus, we will think of arc length as the length of a piece of any curve. Our goal is to find a formula for the length of this blue arc. We will start by using the length of this segment as a very rough approximation. Let's call the length L. If we call the change in x delta x and the change in y delta y, we can find an expression for L using the Pythagorean theorem. L squared equals delta x squared plus delta y squared. So our rough approximation of the arc length would be the square root of delta x squared plus delta y squared. But this would be a very poor approximation. As is often the case in calculus, we can make a better approximation by calculating several tiny lengths and then adding them all up. When we are dealing with tiny segments, instead of talking about the delta x and delta y, we use dx and dy. We will not get very far in our calculations if we leave dx and dy separate. All the magic happens when we have dy dx, because that means derivative. We can cause the more useful dy dx to appear if we divide all three sides by dx. So far we have this. Let's apply the Pythagorean theorem to this triangle and see what we get. Our goal is to solve this equation for L. The next step would be to unsquare the fraction by taking the square root of both sides of this equation. Then we can get L by itself by multiplying both sides by dx. So here we have found an expression for length L. Remember that L is just a tiny piece of this arc. If we want to approximate the whole arc length, we need to add up all of these little segments between A and B. And in calculus, if you want to add up many tiny parts, you do it by integration. So we need to integrate all of the L's from A to B. In this case, we are moving from left to right, so we will do it with respect to x. If we take our expression for a tiny segment L and add up all of the segments by integrating from A to B, we now have an expression for the entire arc length. We will now call it lowercase l. This is one version of the arc length formula, and you need to memorize this. This formula gives you the length of a portion of a curve from A to B. All you need is the derivative. The arc length formula we just derived was written with respect to x. If we want to derive the formula that is written with respect to y, we need to divide the three lengths by dy instead of dx. Now we have this. Let's set up the Pythagorean theorem and take the square root of both sides like we did before. Now we have this. Multiplying both sides by dy gives us this. And if you add up all the tiny l's through the magic of integration, you get the version of the arc length formula that is written with respect to y. Remember, if you have dy dx, then you are integrating with respect to x. If you have dx dy, you are integrating with respect to y. You will sometimes see the arc length formulas written like this. No time like the present. Go ahead and pause your screen and memorize these formulas right now. Example 1a. Find the length of y equals x squared from x equals 1 to x equals 4. Set up but do not evaluate. To set up the arc length formula, we first need an expression for dy dx, which is 2x. So the arc length from 1 to 4 would be given by the square root of 1 plus 2x squared dx. Here's a picture of the length we just found. Example 1b. Find the length of x equals the square root of y from y equals 1 to y equals 16. Set up but do not evaluate. X equals the square root of y is the same as x equals y to the 1/2 power. Since this time we will be integrating with respect to y, we first must find dx dy, which is going to be 1/2 y to the negative 1/2 power. So the arc length is the integral from 1 to 16 of the square root of 1 plus dx dy squared dy. Notice that this is the exact same length of the exact same curve from part A. Example 2a. Find the length of y equals arcsine e to the negative x from x equals 0 to x equals natural log 2. First, let's find the setup with respect to x. In a moment we will need dy dx, the derivative of arcsine, but let's remember the memorized rule. The derivative of arcsine u is 1 over the square root of 1 minus u squared, and then because of the chain rule we have to multiply by u prime. In this case u is e to the negative x, so u squared will be e to the negative 2x. We have to multiply by u prime. The derivative of e to the negative x is negative e to the negative x. There's a little further chain rule here. We have to multiply by the derivative of negative x, which is negative 1. This is the same as negative 1 over e to the x times the square root of 1 minus e to the negative 2x. Here is the arc length formula written with respect to x. I'm just going to put all of this in here. So this is an expression for arc length written with respect to x. In order to write an arc length expression with respect to y, we must first rewrite the expression for the curve with respect to y. Let's start by taking the sine of both sides of this equation. So far we have this. The goal is to get x by itself. We have to get rid of this e by taking the natural log of both sides of this equation. For a split second we have this, but the natural log and the base e are inverse operations which cancel each other out, so we will just have negative x left. Dividing both sides by negative 1 gives us x is equal to negative natural log sine y. Before we can set up the arc length formula, we need to find the derivative dx dy. I'm going to bring down the negative sign in the front, and we know the derivative of natural log u is 1 over u. But then because of the chain rule, we need to multiply by the derivative of u. The derivative of sine is cosine. Notice this is the same as negative cotangent y. If we want to write the arc length with respect to y, we need to change both of these x values to y values. The y values will be given by this expression, so y at 0 will equal arcsine e to the 0. E to the 0 is 1. To evaluate arcsine, we ask ourselves the sine of what angle is equal to 1, and the answer is pi over 2. What about y at natural log 2? For a quick second, we have this. We would really like this base e and natural log to cancel each other out. But for that to happen, we need to do something about this negative sign. We can use the properties of logarithms to move this negative as the exponent of the 2. Now the base e and the natural log will cancel each other out, and we'll be left with 2 to the negative 1 power. Of course, 2 to the negative 1 power is the same as 1/2. To evaluate arcsine 1/2, we ask ourselves the question, the sine of what angle is equal to 1/2? And the answer is pi over 6. Now we can write the arc length formula with respect to y using this derivative and these limits of integration. Be careful, even though the integral with respect to x was written 0 to natural log 2, the integral with respect to y will have to be written pi over 6 to pi over 2. it always has to go from least to greatest, and pi over 6 is less than pi over 2. So this is one version of the answer, but this does simplify quite a bit. First of all, when you square something negative, it becomes positive. So we could write it this way. Better yet, if you remember your Pythagorean identities, 1 plus cotangent squared is equal to cosecant squared. So now we have this. But better still, the square root and the squared cancel each other out. So this is the simplified version that you would probably find as an option on a multiple choice question. For example 2 part B, we are asked to actually evaluate the easier integral without a calculator. Our first job is to decide which one of these integrals seems easier to solve. Obviously, the red one. And this is a good example of why sometimes it's easier to integrate with respect to y rather than x. For this integral, we need the memorized rule that the antiderivative of cosecant u du is negative natural log absolute value of cosecant u plus cotangent u plus c. This is a definite integral, so we need to take the antiderivative and apply the limits of integration from pi over 6 to pi over 2. So we need to find the value at pi over 2 minus the value at pi over 6. Here's the value at pi over 2 minus the value at pi over 6. Obviously minus a negative is a plus. Cosecant is the reciprocal of sine. The sine of pi over 2 is 1, so the cosecant is the reciprocal of 1, which is also 1. Cotangent is cosine over sine. Cosine of pi over 2 is 0, and sine of pi over 2 is 1. 0 over 1 is 0, which we didn't really need to write down. The sine of pi over 6 is 1/2. The cosecant will be the reciprocal, so 2. The tangent of pi over 6 can be expressed as radical 3 over 3, or 1 over radical 3. So I'm going to think of it this way, so I can do the cotangent, which is the reciprocal, which is radical 3. The natural log of 1 is 0, so this term is going to disappear. That's as far as we can go, so the arc length is natural log 2 plus radical 3. Example 3. Find the length of this curve from x equals 1 to x equals 3. Evaluate your integral without a calculator. First, we need to find dy dx. Let's leave the 1/8 out in front, and then we will take the derivative term by term. The derivative of 8x squared is 16x. The derivative of natural log x is 1 over x. If we distribute the 1/8, we get 2x minus 1 over 8x. So here's an expression for the arc length from x equals 1 to x equals 3. To have any hope of evaluating this without a calculator, we need this radical to go away somehow. So our strategy will be to simplify this part of the expression and hope that it turns out to be a perfect square so that the square root will cancel it out and simplify. Please remember that you cannot just square these two terms separately. To get rid of the parentheses, you need to multiply a binomial times a binomial. 2x times 2x is 4x squared. 2x times negative 1 over 8x is negative 2x over 8x, which simplifies to negative 1/4. Negative 1 over 8x times 2x is the same exact thing we just did, so we get negative 1/4 again. And negative 1 over 8x times negative 1 over 8x is positive 1 over 64x squared. Negative 1/4 minus 1/4 is negative 1/2, and then 1 minus 1/2 is positive 1/2. With luck, this trinomial will turn out to be a perfect square, and it will factor as the same binomial twice. So let's shoot for that and just see if it works out. 4x squared would then factor as 2x times 2x, and 1 over 64x squared would factor as 1 over 8x times 1 over 8x. The question is, if we actually multiply this binomial times itself, will it give us the original trinomial? Because of the way we picked the 2x and the 1 over 8x, we are guaranteed to get the 4x squared and the 1 over 64x squared. The only thing we have to worry about is the middle term of 1/2. So we just need to make sure that the inner terms plus the outer terms give you this middle term. When I say inner, I'm talking about the product of these two. So if I multiply 2x times 8x, that gives me 2x over 8x, which reduces down to 1/4. So for inner, I have 1/4. Well, what about outer? That's the exact same product. So of course I'm going to get 1/4 again. And 1/4 plus 1/4 is 1/2. In other words, inner plus outer does equal the middle, so this works out. So more compactly, we can write the original expression as this. Remember, this original expression represented everything that goes under the radical in the arc length formula. So the arc length from 1 to 3 is given by this. The radical and the exponent cancel each other out, and we have this. To find the antiderivative, it might be easier to picture it like this. So the antiderivative of 2x is x squared. And the antiderivative of 1/8 times 1 over x is 1/8 times the natural log of the absolute value of x. Next, we apply the limits of integration from 1 to 3. So we need to find the value at 3 minus the value at 1. Here's the value at 3 minus the value at 1. Natural log 1 is 0, so this term is gone. So we really just have the first set of parentheses minus 1. 9 minus 1 is 8. So the arc length is 8 plus 1/8 natural log 3.